Hello students, today we'll talk about electrostatic potential of point charge. Last time we understood the concept of electrostatic potential. Now there are so many different possibilities. We may have many charges in a system, we may have distributed charges in a system. So how do we find out influence of these charges at given point? We'll start with point charge. Today we'll talk about influence of point charge in its surrounding, and we'll understand how to find out electrostatic potential of point charge. And then in the next videos we'll talk about system of many charges or maybe distributed charges. So today just one small topic: electrostatic potential of point charge at given point. Let us start. To understand today's topic, we should be knowing the definition of electrostatic potential. We know that electrostatic potential is defined as work done to bring unit positive charge from infinity to given point in the electric field. And how do we express electrostatic potential? We know that it is work done per unit charge, so it is W by Q. Which work we are talking about? Work done to bring small q from infinity to given point. And we also know that when you are talking about absolute potential is when charge is brought from infinity. So integration is from infinity to a point. So if you are bringing from infinity to given point, initial potential energy or initial potential is zero, and hence it is called absolute potential at point A. But if you are coming from some other point in electric field to a point, say point B to A, then it is called relative potential at point A due to the source charge. Okay, so I assume that you have understood these topics, and then we are eligible to go to today's topic. So let us start. Consider a Cartesian coordinate system with coordinates with the axis x, y, z as shown here, and let O be the origin where we will place our source charge capital Q. Let there be some point P where we want to find out potential. So I want to find out potential at this point due to this source charge capital Q. So as per the definition, what I have to do? We assume that position vector of point P is Rp. Okay, so I want to find out potential at this point P. What to do? So recollect the definition of potential. It says that potential is work done per unit charge. So I have to get my unit positive charge, and then I have to bring unit positive charge from infinity to point P. So let us consider this as infinity, very far distance where we are with our unit positive charge, and from there we will come to point P. Now as we come to point P, we know that the electric field of Q will be different at different point. Electric field of Q here, electric field of Q at this point, or electric field of Q at this point, or electric field at this point will not be same. So if I consider the work done to be F dot dr, or force if we write as QE, then QE dot D, if we consider E is not constant, and hence what we will have to do? We will have to take dW. What is dW? Work done corresponding to small displacement, we may say. So we consider a small part of journey where, say, at distance r. So at r distance I have chosen small part of the displacement, let it be dr, and first we will find out work done for the small displacement. What is dW? Work done to move our unit positive charge from this point to this point. What is the advantage? For this small part we may consider electric field to be constant, and then we can apply this equation. What next? Okay, once you find out dW, integrate from infinity to P. integrate from infinity to p, and you will have total work done. Okay, so with that logic we'll go further. And when you consider dr, you can define electric field also. How much is the electric field at r distance? We know it is k q by r square. Okay, be careful, this k should be small k. Okay, so k cube r square, we know electric field, we know displacement dr, so we should be able to find out work done and then integrate. So with that logic, let us go further. So here is the situation. What is the situation? We are coming from we are coming from infinity with our plus 1 coulomb charge to point p. Okay, and as electric field is changing, we cannot find out work done in one go. And so first we'll find out dw. What is dw? dw is work done corresponding to small displacement. How much small? Say dr. Okay, where you have chosen your dr? We have chosen our dr, small displacement at distance r. How much is the electric field at r distance? K cube r square. So I think we have all the necessary values to find out dw. And once we have dw, we can integrate. So what is the electric field? So electric field can be given as kq by r square, and unit vector r is indicating direction. So if this is the direction of electric field, we are coming in this direction. So if this is dr is in opposite direction to the electric field. So dr, if I write, it has to be minus r cap. Why minus r cap? Because electric field and displacement both are opposite. Okay, so direction of displacement is considered minus r cap and direction of electric field is plus r cap. So let us try to find out work done now. So we know that work done is force dot displacement, and what is force? Force is QE. And we substitute values of electric field. This is electric field from equation 1, obviously with Q. Q is brought from here, and displacement in terms of magnitude and direction. So unit vector r and unit vector r will give 1, and minus sign can be taken outside with the constant terms also. What is the integration of 1 by r square? 1 by r square on integration will give you minus 1 by r. So now we have minus kqq and minus 1 by r. So minus minus will get us plus. Substitute upper limit and lower limit, you will have 1 by rp minus 1 by infinity. Obviously 1 by infinity is 0. And so work done is kqq by rp, that is product of the two charges and distance in denominator. This is the work done, not potential, not potential. What is this? Suppose if the answer is 10 joule, I am saying that to bring charge small q from infinity to the point at distance rp, I have spent 10 joule energy. Okay, but my charge may be 1 coulomb, 2 coulomb, 3 coulomb. So my answer depends on the small q, and so we divide answer with small q. And as per definition also, potential is W by Q. So these are the equations from previous screen, and now potential is W by Q. Substitute 3 in 4, what you will get? Work done depends on small q. Work done obviously depends on small q, the charge which is being brought. But we don't want our answer to depend on the charge which is brought, so we divide answer with q, and then what we get is kq by rp. Look at this quantity, look at this. It depends on the source charge, it depends on the charge we are interested in, it depends on the distance. So potential of a point, it depends on source charge, it depends on distance. One more quantity it depends on is k. What is k? 1 by 4 pi epsilon 0 means it depends on the medium. Okay, if you place capital Q in some other medium, potential will not be same as the given as what we get here. So in general, electrostatic potential is given as kq by r. Okay, so kq upon distance, whichever distance you are talking about, more the distance, less the potential, and it is very obvious also. As we go away from the charge, influence of the charge decreases. But unlike electric field, here the decrement is linear. Recall the expression for electric field. Electric field is kq by r square, whereas potential is kq by r. It means that electric field decreases drastically as you go away. The relation is 1 by r square, whereas potential decreases linearly as we move away from source charge. So we consider a slightly different situation. Now we don't have capital Q source charge at origin. Let it be at some position vector r, and the point P is at position vector r prime. How do we find out potential of Q at P point now? Now the expression has not changed, values are changed. What is the expression for electric field? Sorry, electrostatic potential. It is kq upon distance. What is the denominator? Kq upon distance. Now, how much is the distance right now? How do I find out distance of point P? So it is the mod of resultant vector r minus r prime. R minus r prime is the resultant vector, and what if I take mod of this? It will give me distance between Q and P. So for this situation, electrostatic potential can be given as kq upon distance, which is r prime minus r, or r minus r prime, makes no difference as long as you consider mod. So this is how we can express electrostatic potential of any charge at given point. Let us now compare electric field of point charge and electrostatic potential of point charge. How many points of comparison we have? So we know that electric field is defined as force experienced by unit positive charge, and as force is vector quantity, potential is also vector quantity, isn't it? Whereas when we talk about electrostatic potential, force is vector quantity, so electric field is also vector quantity. In case of electrostatic potential, it is work done to bring unit positive charge from infinity to given point in electric field. So work done we are talking about, and work done is scalar, so potential is also scalar. How do we express electric field? Electric field is expressed as if we talk about electric field of charge q at distance r, it is f by q, so kq by r square. And if you are talking about electric potential of q charge at r distance, how do we express it? It is w by q, so kq by r. Look at these equations. Electric field is f by q, potential is w by q, electric field is kq by r square, potential is kq by r. Further, if we go, unit of electric field is force upon charge, means Newton per coulomb or volt per meter, whereas unit of electrostatic potential is joule per coulomb or volt. Electric field is vector quantity and electric potential is scalar quantity. Very important difference. Understand that electric field is also influence of charge, electric potential is also influence of charge, but electric potential is slightly easier quantity to deal with, easier to handle, okay, as compared to electric field. Now if I have this situation, once again we consider the same situation. Suppose I have charge q and point P. How do I find out electric field of q charge at P point? So when we talk about electric field, I'll need distance square And when I talk about potential, I'll need distance between Q and P. So how do we express? In case of electric field, I'll also need to know the direction. So how do we express electric field? How do we express electric potential? So electric field can be given as KQ R prime minus R. Okay, we don't have terms corresponding to this in potential. So when you are writing electric potential, it is expressed as KQ by mod of R prime minus R. Okay, so this is the basic difference between electric field and electric potential. Okay, so let us conclude now. Electric potential of charge q at distance r can be given as kq by r, kq upon distance, whichever point you are talking about. Just see how far the point is from the source charge. Electrostatic potential is scalar quantity, and it depends on how many things. It depends obviously on which charge you are talking about. If magnitude of charge is more, potential is more. Compared to 2 coulomb charge, 5 coulomb charge will have more potential at same distance. Secondly, it depends on the distance. As you go away from charge, potential decreases, very obvious. And thirdly, medium has also its own role to play. If you change medium, potential of the given charge at given point will change. And what is the distance dependence? We know that V is proportional to 1 by R. So electric potential of point charge is inversely proportional to the distance of the point where we are finding out electric potential. So that is all we need to know about electric potential of point charge at given point. Thank you.